Now, I have made up my notes. I will put them up. It's by the end of this week. A lot of it has been written down. But remember, this is the first draft, and it will go on changing as with time, and as well as your inputs are important. Now, a relation is the first thing by which we put some kind of a structure. As I was explaining to you last time, that there is a unknown notion of a structure in all of us. But again, we will not try to define what a structure is. We will see several structures though, and we will understand what is it very soon. So the first what do you say, tool by which this is introduced is the notion of a relation. So let's look into, say, two examples. Say, the first one, say, the very familiar one, say, is a factor of. So we usually write this as, so 2 is a factor of 4. So saying like this, with a line in between, is a factor.
Sorry, Doctor.
Yes?
Are you sharing the screen already?
Did I not?
Yes.
No.
I can see it.
Oh, can you see it?
No, myself too, I can't see it.
Okay, I shall share the screen again. Is it viewable now?
No.
No.
Julia, can you see it?
Yeah,
I can't see it, yes.
I'm on a computer, if that helps.
Yes, I'm also on a computer.
Myself too?
So you didn't do anything to activate the screens, Julia?
No, I just,
Did it just appear?
it appears every time the doctor shares, yeah.
Yes, yes.
If you look at the doctor's icon, the P, does it have a little TV screen at the bottom?
Yes,
bottom
it
right
does.
of it?
Yes.
Let's see if that works. Try and click on that to see what happens. Or just click on his icon and see if it changes.
It says participant has stopped the camera.
Okay, that's strange.
If I click on it.
Maybe you guys need to rejoin. I don't know.
Okay. But Doctor, I think you can carry on. We will try to listen. The factors of 2.
Okay. So is a factor of, so 2 is a factor of 4. But 2 is not a factor of 5, right?
Yep.
Now how do we capture this? So we collect all those pairs of integers, belongs to Z cross Z, such that P is a factor of Q. Okay? Or we can also write this
I'm going to try to rejoin to see if I can get the screen, Doctor, okay?
okay. So collecting these pairs, so you see, as we said, a set is actually another name. It's another name of a property. So this set, therefore, is actually the name of the property is a factor of. Okay? We are just collecting those pairs in Z cross Z such that the first coordinate is a factor of Q. Therefore, it is immediate that 2, 5 doesn't belong to this set, but 2, 4, 3, 6, 2, 8, they are all in this set. Okay? So this is one way. Another way is, and this is actually how it is implemented also. Say we have databases of employees. So usually how is it done? So there can be several departments or projects in which a company runs and several employees. So how is it implemented? So each attribute, it is called, so employee and an attribute, say the department or division. So such pairs of data are stored. And there will be many. So there will be M division, I'm just looking into 2. So now the collection of these pairs precisely tell me which employees belong to which division and so on. Okay. So it is actually, therefore, the formal representation here when we are doing sets is this, a relation from a set A to a set B, or we also sometimes say between A and B, is a subset. So the relation is completely determined by this subset. Specifying subsets of Cartesian products are nothing else but just giving relations. Now let us look into some examples. Obviously, the empty set is always a subset of A cross B. And this is called the empty relation. And A cross B is always a subset of A cross B. It's obvious. This is called the whole relation. But now for something else. Suppose you have R. You have another relation R inverse. By the way, there is a common convention. Instead of writing xy in R, this is one way of saying, it's obvious as we know. Another way of writing it is x and R in between and y. So it says x is R related to y. Okay. Now here, what is R inverse? This is precisely the opposite. So this is Yx belongs to B cross A such that xy is equal, belongs to A. So let's for instance look into this. This is a factor of the inverse relation is a multiple of is a multiple of. So 4 is a multiple of 2 and so on. And you can phrase this one. So this was employee works in this division, and the other one could be division has this employee and so on. So sometimes it is a convenient one. We will see how this is getting. This will get very important very soon. There is another very nice relation, and that is, which is denoted by this, which is a relation on a set itself. So it's a relation amidst the members of the set themselves. So it's a subset of A cross A. We call such things relations on A and so on. So what is this? This is the set of XX. Sorry. So this is precisely, if you can see, this is precisely the, if you can say, this is the equality relation on A. It's another common name for it. It is called the diagonal relation. And the reason for this is, remember, if we try to draw a graph, remember if the diagonal, if this is the x-axis, this is the y-axis, the diagonal is usually this, right? And the diagonal precisely contains the points whose x and y coordinates are same. So keeping that old formalism in mind, it is called the diagonal relation. However, it is ideally to be thought, can be seen as equality. Okay? Now, if R is a relation, from A cross B, and S is a relation on, say, B cross C. So we are going to make a new relation from this, and we usually write this as the composite relation. It is called the composite relation. We usually write this as S composed R. So S is first and then R. So this is the collection of all the pairs X, Z belongs to A cross C, such that there exists a Y in B, such that XY is in R and YZ is in S. This word there exists, we usually shorten it to something like this, an reflected E. So we usually write there exists a Y in B. So this symbol means there exists, such that X, R, Y, S, Z. Okay? This has many applications. We make newer and newer relations with this composition, and we will see how we are going to use this. But now for some nice properties which I have listed. So firstly, the inversion, if you do it twice, you get back the original relation. Okay? Suppose you have R, S, and T. So then S cross R is a relation from A to C, and then you can also put T on that. That is same as okay. So this is, we often say that this relation is often called the composite relation. And we say the composition of relations is associative. Yes? Yes, somebody wanted to say something? And then, well, the diagonal is something very nice. R composed, if you, R is from A to B, so it will be this. This is still equal to R. And on the other hand, delta B composed R is still the same. Okay? And inverse of the composites is, I had S composed R, sorry, is S composed R. It just reverses itself. Now, there are several other properties. Equality of relations is, again, relations are sets, so two relations are same. If as sets they are same, and so it just means that what the things that are you are relating, they're exactly same by the two and so on. How this composite relates with the union and intersection, I have listed them and I have left them for exercise. And next day when we are going to meet, we are going to have some time on your efforts on how to have you proceeded with those exercises. Okay? So, but let's now come to some special kinds of relations. So, yeah?
Hello, Doctor.
Yes?
I no longer see the screen.
Oops. That's quite strange, because is it the same with others?
Me, I'm okay.
I
Yeah.
can see the screen.
Yeah.
So this is Ayub here. First, initially I couldn't see the screen, then I actually logged out again and restarted the whole process. So I think you must go out and then come back in.
Oh,
Okay.
Okay?
Now we will be looking at relations on a set. So that means I have relations now, all are subsets of A cross A. R, S, whatever I say, R is a subset of A cross A. Now a relation is said to be, so the relation is said to be reflexive if for each x in A, x are x. I don't know about others, but at least I have x being related to itself. You can easily see that there are relations which are not like this. For instance, 2 cross 2 is false. So 2 is not less than 2. So less than relation on numbers is not reflexive. Okay? So there can be relations which satisfy this. Alright? There can be relations which satisfy this partially. That means for some x, x are x, but there are others for which x is not Rx. Okay? But reflexivity is demanding that it should be true. X R x must be true for each x. That is the crucial part of the story. Why I am spending a little more time here is you will very soon see the next things which are not that assertive. Okay, so it is said to be symmetric if x or y implies y or x. So it says if x is related to y, then y is related to x. Okay, again, less than is not symmetric. 2 is less than 4, it doesn't say that 4 is less than 2. So you can see there are asymmetric relations. But remember, this is an implication statement, right? So it doesn't say, for instance, the empty relation is symmetric. Can you see this then, therefore? Is it clear?
Yes.
Because the hypothesis is false. Right? X empty set y, yes, x, y belongs to the empty set, that is false. So this implication statement is true. So the empty set is symmetric. So see the difference between the two properties. The first one is an assertive one. The empty set cannot be reflexive. The empty relation on a non-empty set cannot be reflexive. Okay? But it is symmetric. Okay? So that's the most of the definitions you have to be careful to distinguish. So in a definition you have to be careful to distinguish between statements which are assertive, some things which are like this. These are assertive. These are, let me make a note. This is an assertive sentence, and this is an implication statement, as I already said. Now, implication statements are, well, they also assert something, but it has the problem of vacuous implication. So you have to be careful. But assertive statements are very strong. It says, it tells you that something is going to happen. Okay, so that's not quite true for implication statements because of this vacuous implication. Okay, it is said to be antisymmetric. It is said to be antisymmetric if x are y and y are x. If both of them happen, then x is equal to y. Okay, so for instance, this is the kind of situation which we have for less than or equal to. You remember, x is less than or equal to y and y is less than or equal to x x implies x is equal to y. This is usually the way how we even. So there are some relations which are antisymmetric, but less than is not antisymmetric. Okay, so there is something called transitive. If x are y and y are z, implies x are z. Okay, so again, less than is a typical example. Okay, so then let's come to it is said to be an equivalence relation if it is reflexive, symmetric, and transitive. It is said to be a preorder if it is reflexive and transitive. And a partial order if it is reflexive antisymmetric and transitive. Okay, we will come across these relations again and again, and there are several other kinds of relations, but I have just made a list of the most of the ones which are most commonly used or required and so on. Let's have there is another aspect that I want to highlight upon is usage of the calculus. The word calculus means a set of rules. Now, these definitions that are given are in terms of points, right? And often checking in terms of points make it very, very difficult and very specific. But if we have a calculus, then And if we can develop a calculus, so that makes our lives simpler. Okay, so it's a set of rules, we check for those and then we. So here are some nice rules, some calculus. A relation is reflexive if and only if it contains the diagonal relation. This is nothing else but rephrasing the. Remember, reflexive means if and only if for every x, xx is in R, but that xx is actually a member of the diagonal relation, and hence the diagonal relation becomes a subset of R. Okay? So it is symmetric if and only if, although we write it like this, it turns out that both are same. So this or okay. So it turns out, so that means, as you can see, so the inverse relation has some way to express the notion of symmetry. Now here is a transitive. This is where the composite comes into the picture. And these are given in the notes as and left as proofs. So next day we are going to look into these proofs. But I need your attempts. Okay? Again, it's very simple. Now, the next thing that is, this calculus helps us to find the smallest, say, I am given an arbitrary relation, but I can find the smallest relation which is, say, reflexive, but contains. So the goal is now, given the relation R, so the question is, does there exist a relation S which contains R and has let me say good property. Where what is the measure of goodness? Well, any one of these 7 things. Okay, so reflexive. So one of the good properties is being reflexive. So one of them is symmetric or transitive and so on. So I want to ask the question first, does there exist one such relation which contains R and is? And then we sharpen this. You see, usually we always want to find the best such. So what will be the best such? So to find the smallest relation S, which has the good property. And we will see that there is a pattern in every place, in every quest. We are asking almost similar things. Here it is quite concretely we are asking whether there exists a relation larger than that, and the smallest one, which is larger than R and has the good property. But there will be several ways, several statements. You will find that there is a this kind of statement coming up again and again and again. And we will have this formalized later on. But let us see. So I have a relation R. Let's try and figure it out. So let's try to make a picture. As we agreed that this is the diagonal relation, right? So our first observation over here tells us a relation would be reflexive if it is like this, right? So if it contains the whole of the diagonal, right? Clear?
Yes.
You see how am I drawing subsets of this? So regions, so things like this, therefore give us, so if this is my R, so this is giving a reflexive relation, right? That is the picture of a reflexive relation. Okay? Whereas here is a picture of a non-reflexive relation. I do this. And here is a picture of a non-reflexive relation. Right? Or here is another such picture. Or even their union, if you take the union of these two. Both of them are not reflexive. For R, no one of this is true. For S, some XX, but not all. Okay? So both of them are non-reflexive. Now, can you make a relation R, say a relation T, which is larger than R but is reflexive? What does it suggest? What does the picture suggest? Can you make a relation T which is larger than R? So I need T which is larger than R and T is reflexive. Can you
you can do it in the left hand side drawing. If you've got R and you could possibly have T that includes R but has more of its own stuff, and then R would be a subset of T.
Yes, you're right, but R itself is reflexive. right? In on the left hand side. But here, so why would I then increase it? Okay, anything bigger than a reflexive relation therefore is a reflexive, right? But the question, but here on the right hand side, R is not reflexive. But can I make a relation which is bigger than R and yet is reflexive? Use this calculus, use this picture, and come to your. Okay, I'm using 1A. Let's give a hint. So T is reflexive means this is the other way of saying it, right? Okay? Reflexive, that's 1A, if and only if. Okay? So it's reflexive if and only. So that's the picture which suggests on the left. Okay? So T is going to contain the diagonal. But you have told me T is also containing R. So T must contain the union, right?
Yes, that makes sense.
Okay, but hang on, R union this is also containing this. So by 1A, R union delta A is a reflexive relation. Okay, and that is the smallest one. So the smallest reflexive relation, so we immediately conclude the smallest reflexive relation containing R is okay, clear?
Yes.
Yes.
Okay, now let's look
Can
at
the entire
yes
can the entire set be reflective to its own self?
yes, obviously anything which contains the diagonal is reflexive. So this full set A cross A, it also contains the diagonal, it is reflexive,
Okay.
right? Okay,
Yeah.
now let's see about the next one. Let's try and see. Symmetry can still be given a pictorial depiction. And here I am obviously going to use it was bad. Okay, now how do I get the inverse? So suppose I have this relation. It drew it very symmetric. Oh no, it was fine, but still okay. How do I get? Remember, if you have a coordinate and you take its reflection along this diagonal, you get its yx, right? If this is so I'm going to use that geometry. So using that geometry, if this is your relation R, then your R inverse is, it will be difficult, but I don't have okay, it's almost, but yeah, almost the reflection. So if this is your R, then this is your R inverse. So this is obtained. So this is obtained by reflecting R along the diagonal. Okay, so that's the idea of symmetry. So you can see when the diagonal is a line of symmetry of R, that's what symmetric relations are. So and that's exactly what this is saying. This thing is saying that relation is symmetric this means, how do I say, the diagonal is a line of symmetry. I wrote this within quotes to mean that it is a very informal, intuitive picture. Okay, but this picture often helps. So how will you get, so now see, as I have drawn, this R is not symmetric. So if you reflect it again, it will not be symmetric. So now my question is, I want to find a T which is bigger than R and T is symmetric. Can you use the diagram to say what would be, how would you get hold of T?
Can't we consider the intersection?
Okay, if you can consider the intersection, observe it is this part only, and then that intersection cannot contain R. The intersection is smaller than R. Okay? So the intersection will
Would
not...
we need to find something like R, the inverse of R is a subset of R, and that is a subset of T. That would give you a...
But here, for a general thing, R inverse is not a subset of R. So...
yeah.
Yeah? R is symmetric if and only if R inverse is a subset of R or R inverse is same as R. So that's the criterion for symmetry, which if you look into this diagram, it tells what it is meaning. So now my question is, I have given you a general R. Looking into this scheme of reflecting it along the diagonal, how can I find a T, a subset T, which would have the diagonal as its line of symmetry and would contain R? Obviously there is one, you can see. The whole thing is obviously that. Okay? Try to make it smaller. How small can you make it? Yet having the line of symmetry. Now the diagonal is the line of symmetry.
It's like T has to contain the domain and codomain.
I don't want to bring. I have not.
Something like that.
Yeah, I didn't bring in these terms, although I did it in my notes. But even then, without the domain and codomain, you can see. Okay, let me give you again. Yeah.
If you intersect it with the diagonal.
See, the intersection is a procedure which makes it smaller. Right? The set is going to be reduced. I want something bigger. So whenever we are looking for something bigger, we want to have more things. So we have to take unions. Okay? So idea is this: whenever you want to make it bigger, one way to make it bigger is by taking unions. Now, okay, so don't think along the terms of intersections. How can you see in terms of unions now? So
if you consider the union of the complements of both sets.
if you take the complements of both the sets, good. So that means the complement of the both the sets, that means it is nothing else but the complement of the intersection, right? We know that you want to set the union of this, but this is nothing.
Yeah, then
that is nothing else but this. Okay, so that means everything which is beyond, which doesn't contain this middle part. So that thing, okay, that is something bigger, I understand. It's a big set, but it doesn't contain R because you have already thrown out this middle part.
Can we say that T is the union of R and the inverse R?
Good. Yes. Yes. If you now keep this reflection and now think of the figure which consists of the original figure as well as its reflection, then obviously this total figure has the diagonal as its line of symmetry, right? This whole thing, this whole thing in this third color, orange or whatever, obviously has this as has the diagonal as the line of symmetry. So a plausible answer should be R union R inverse. But let's see. Yes, it is. That is the thing. T is symmetric, right? So T inverse, that is equal to T, that contains R inverse. So you see T contains both R and R inverse. So T contains R union R inverse. And this is one fact which I didn't say now, but okay. But you can see it from this diagram that R union R inverse, the inverse of that is itself. Okay. So the inverse of this is R union R inverse. So this is and this is symmetric, and this is the smallest symmetric one. Okay. And in my notes I have given a description of the smallest transitive relation containing R. It is called the transitive closure of R. This is called the reflexive closure of R, and so on. But transitivity is something which is, I'll not say it is not geometrically possible to say it, but it will require a third, so it will require a third dimension. Okay, so, and it becomes a little bit difficult to draw. But if someone can view it in terms of these cubes, it is fine. But often, as I for myself, or you will find it also very convenient to, instead of going through this geometric pictures or through these definitions, it is much easier to go via this calculus. And I have given the explanation in my notes about the transitive closure. It's better that you give it a reading and then we speak about it. It's a process. So let me quickly just say, how will you make it? Well, what do you need? What are the things that you need to add? Remember, if you have x, r, y, and if you have rz, then it should mean that x, r, z. That's transitivity. Now, you start off with one element x. So, you bring in a y, which is related to it. Then you bring in another z, which is related to it. But you don't know whether z is related to x, right? So, when you get such a triplet, you have to put in xz. So you have to include. So that means, what are the things that you have to include? So R union xz. I'm not saying. Okay, then next stage, yes, you have to do that again. Z prime. You have to have yz prime, you have to have xz prime. Okay, and so on. You have to add all of them. So that so that means this whole idea says, if you have a chain, if you have a finite chain of such things, each one of the pairs that you can take, they are all related. That's okay. So when you take a finite chain of such things, each one of the pairs that you can make from that, in whatever way, without disturbing the order. Okay. So each one of these pairs must be there, and this has to be done for all possible chains and starting from all possible x's. And so we will have to make sets or make describe a process which does this for chains of length 1, of length 2, of length 3, of length 4. So we have to add all of these. So how do I make a chain of length 3? Chain of length 3 is R composed R. Chain of length 4 is R composed R composed R. Okay, and so on. So all of these have to be made, and then the next thing is obvious. So I'll leave it to you to go through that, and let me see if leave it to you to go through those notes, and then we will come back to it along with the leftover things that have been left over there. So next day we will actually start with those open ends that have been left today. Okay?
Okay.
So I stop the recording here. So